19.6, almost 0.6 millisievert due to the use of radiation in medicine. 0.4%, around 0.01 millisievert, is due to the other sources of man-made radiation. Evidence of an increased cancer risk in humans is available at doses above 100 millisievert. Below this dose, an increased risk has not been identified through many studies. The nominal risk coefficient for radiation-induced cancer incidence is 5.5% per sievert. If we multiply this by the individual dose of 0.1 millisievert per year from drinking water, gives an estimated annual cancer risk of approximately 5.5 per million, which means that's very, very small number. Therefore, the individual dose criterion of 0.1 millisievert per year represents a very low level of risk that is not expected to give rise to any detectable adverse health effect. And thank you.
Thank you very much, Dr. Sharaf. With your permission, we will continue with the presentation and then have about 20 minutes or 30 minutes at the end for discussion. Thank you. Thank you. Thank you very much. Thank you very much, Dr. Sharaf. I would like now to introduce Professor Jawad Al-Bakri. Professor Al-Bakri is a professor at the Department of Land, Water and Environment at the University of Jordan. He has about more than 16 years of research focusing on remote sensing and geographic information and the application of remote sensing and geographic information in land resources management, including the assessment of climate change impacts on land and water resources. He has worked on several assessment studies, including the impact of climate change on food and water security. That was through the second National Communication to UNCCC, and also worked on the FAO MDG project. He's participated in 2 national projects for improved water management through the use of remote sensing. Projects implemented by the Ministry of Water Resources and Irrigation with the partners of NASA and GIZ. Has focused on the modeling irrigated areas, crop water requirement, climate change, and drought. His teaching experience also includes courses on GIS and remote sensing and environment at the University of Jordan, German Jordanian University, and the University of Cologne, ITT. I would like to welcome Professor Al-Bakri, and if he may join us, please. Professor Al-Bakri, just click on the hyperlink and your presentation.
Okay, thank you, Chairman. Good morning, everybody here, ladies and gentlemen. I will start from the last point, which the Chairman talked about, which is about the use of geospatial techniques in water management. So the presentation is a summary for our work which has been accomplished last year with the cooperation with GIZ. I will start with background on use of remote sensing and GIS at the Ministry of Water and Irrigation. This is not, I will say, an old era of use of remote sensing and GIS. But in the last 3 years, I think the Ministry of Water and Irrigation moved a very important step towards the adoption of these geospatial techniques. I will present my case study in year 2016, which is about monitoring of groundwater abstraction in the highlands of Jordan, and what were the main findings and the conclusion. Why the Ministry of Water and Irrigation started to think about geospatial techniques? Because the technology is improved with time. Now there is lots of Earth observation systems with their data available with no cost, nearly no cost, or at low cost. And the other thing is the integration of geospatial data, remote sensing, and GIS, and their use in different models for water monitoring and assessment. And I will say, maybe from my teaching experience at the University of Jordan and outside Jordan, that this technology is attractive for the new generation. So when you go for a department of soil or water, you will see that the course of remote sensing and GIS is attracting for the new generation. There are many mobile applications now which involve the use of GIS and remote sensing. So with the use of automation and digital analysis, I think the technology can provide lots of useful information and tools for the water management issue. Now, when we go for the Ministry of Water and Irrigation, the use of remote sensing data and GIS is not, I will say, is not a new experience, but during the last 3 decades, the use was mainly focused on mapping, only mapping of water resources, ground and water and surface water resources. At the Ministry of Water and Irrigation, each firm or part of the ministry has its own GIS application. So if you go for Miyahuna, for example, they are focusing on their geodatabase, on the network analysis and their data. If you go for the other, let's say, firms of the Ministry of Water and Irrigation, the mapping is focused on the surface water resources and so on. This is my personal judgment that the concrete steps, if we go to the Ministry of Water and Irrigation, started about 5 years ago through a World Bank project and a partnership from NASA, in which they started to use and establish a unit of remote sensing and GIS at the ministry. The application within this project started for crop mapping for 2 pilots, Azraq and Mafraq, and there was a trial which I supervised, trying to uncover the violation of water use, the access to illegal water sources, or the illegal access, I will say, to the water resources, and then develop the work to assess the groundwater abstraction records, which is the case I'm going to present. Now, one point which started at the Ministry of Water and Irrigation is upgrading their maps, updating their maps of the irrigation in the highlands mainly, because in Jordan Valley, I will say that the issue is much easier because we have the farm units which are identified, and you can know what is cultivated there or irrigated. But if you go for the highlands, I would say it's more difficult. The estimation of crop water consumption is also another issue that the Ministry of Water and Irrigation is working on. The first pilot that I'm going to present on 2 areas mainly, the detailed mapping of irrigated areas, and the three areas, one in the Azraq Oasis, the other one in Mafraq, and the third in Ramtha in the Yarmouk Basin. So we started the mapping and producing the irrigation map for these pilots. In this work, we have used the digital classification, and we used the Landsat 8 data. We took about 1 year of satellite images, about 20 images per year, and we carried out the whole processing. During that period, I started the on-job training for the staff at the Ministry of Water and Irrigation and how to use these data and multi-temporal images to capture the irrigated areas. The thing which was attractive at that point is to estimate the crop water requirement. And with the maps, we tried to estimate the crop water requirement using the standard method of FAO 56. But the problem with that method, it's a theoretical method which assumes standard conditions that might not be found at the farm level. So for example, here for one of the areas, if we go for Mafraq, the one which I have shown the map to, we have calculated, or let's say we have used the GIS to estimate the irrigated area. Then after that, what is the net crop water requirement and the gross crop water requirement, and what was the record or the recorded groundwater abstraction at the ministry. And we can see that the actual, or I won't say the actual, it's the estimated actual, was twice the groundwater records. So the figures were a little bit alarming. And we said, because we have used the FAO 56, let's go for another method. And this is what we have done in year 2016 through a support from the GIZ. We have selected 5 study areas and 5 basins in the Highlands. Then we have used the Landsat ATM Plus and OLI. Rapid Eye, which is a German, I think, private company with 5-meter resolution, meteorological records, ground data. And then we started the crop mapping with the time series of Landsat and refined the data with Rapid Eye and the ground surveys. We have included in our work CBAL, which is a well-known model for water auditing. So, but the problem with CBAL, it was mainly used with Landsat 7. So we have shifted to Landsat 8. The other thing, it was not calibrated in Jordan. So we have used some credible data from Ramtha wastewater treatment plant. We have selected some farms where we trust the amounts of groundwater abstraction. And then we have used soil moisture data at one of the stations, which is supervised by the Ministry of Water and Irrigation. So we have compared the groundwater abstraction records with the actual. These are the five selected pilots, one in Yarmouk Basin, the other one in Amman-Zarqa, the third one in Azraq, the fourth in the Mujib Basin, which is in the southern part of Amman, and the last one in Jafar Basin in the southern parts of Jordan. And the green color is the irrigated area in the highland, which was produced from the previous stage. So we have already produced the irrigation map for the highlands, and then we have worked on those 5 pilot or study areas. The remote sensing data that we have used, as I mentioned, is Landsat 8, Rapid Eye, and in the climatic records. The idea with the CBAL model, it's an energy balance model in which you estimate the evapotranspiration, the actual evapotranspiration, as a residual of the net radiation budget. Now, one part of the model with the image processing software, which is shown here for obtaining the surface temperature, in which you have different transformation of the Landsat data into physical parameters. The most important, for example, in this model is the surface temperature and the vegetation indices by which you use, or let's say by which you derive the albedo of the surface. So I'm just showing example. The model is stored in about 15 steps. We have automated the model with the Landsat data. So all what you do is plug the data in, but you need to add the climatic data, and then you calculate the instantaneous evapotranspiration. This is the iteration process for calculation the sensible heat flux, which is the most difficult part of the model. And at the end of the model, you calculate the instantaneous ET, which is the ET at the time of the satellite overpass. So if you divide it by the reference evapotranspiration, then you get the evaporative fraction, or what is known with FAO as the KC. But the KC in such case is the actual KC. It's not a theoretical KC, not like the one in FAO, in which that we discovered that it's overestimating the amount of crop water consumption. So we have carried out and we have carried out the modeling and produced about 20 maps or more for each study area for the KC, or the evaporative fraction, and then we combine them with the meteorological data to obtain the weekly, monthly, and seasonal and annual water consumption. This is one output in which we have the irrigation map for Azraq oasis. You have the wetland, which is dried after January. Usually in January, early February, you have some water, but after that, there's a drop down of water due to the water over pumping. The same area, if you look at the top figure, this is the actual evapotranspiration in millimeter per year or cubic meter per dönum. So you can see that in such area, the actual water consumption might reach about 2,600 millimeter per year. These are for the center pivots of alpha. And we have used some of them for the calibration of the model. The model was a little bit underestimating the evapotranspiration, so we have carried out the calibration for the model using ground data. Now we have used also GIS for groundwater abstraction data to see the hot spots where groundwater abstraction is relatively high. And we have combined the two layers to see whether the recorded wells are going well with the amount of evapotranspiration. This is very important to uncover illegal groundwater wells. And this is the main idea of the work. This is the area in Ramtha. I think there was a campaign in the last year for some of these farms where we discovered that there is a high amount of evapotranspiration without recorded groundwater well. By law, you are not allowed to transfer water or convey water for more than 700 meters, I think, or 1 kilometer. So the illegal aspect might be water conveyance. We have found many farmers, I'm not going to show these photos, but we have found many farmers who are selling water for farms which are about 5 or 6 kilometers from the water source. This is considered as a water violation. So the results here were utilized for uncovering the violation. We have used the Ramtha wastewater treatment plant for calibrating the model as well. This is a very complicated area where I think the campaigns to uncover the violation is still going. This is the area of South Amman, near Qastal and Tanib. This brown spot shows that the amount of water consumption is nearly 5-fold the amount of recorded groundwater abstraction. And I think in the last year campaign, they have discovered that they are connected to the DC line, and they are stealing water from the DC line in some of these areas. So at the end, I'm showing a summary for the work in which we have summarized the total irrigated area, the type of the crop in each, the number of recorded wells, then the recorded abstraction in million cubic meter, then the CBAL ETA, and if you go for the total, you can see that the recorded is 68 million cubic meter, while the actual is about 95 million cubic meter for these 5 study areas. An important point to show that there are also other amounts to add, which are related to the irrigation efficiency. So these are not included in 4 parts of the study area. So if you add the irrigation efficiency, I think you will reach something like twice the recorded amount. So the main findings that the crop water requirements is much higher than the recorded groundwater abstraction. The net is 30 to 50%, excluding the irrigation losses. There's an over abstraction of the groundwater in all basins. I think the worst case was Azraq, followed by Mafraq. Then there's an evidence of violation and illegal access to water sources. The CBAL estimates were less than the actual due to irrigation losses. I've mentioned this, and we are working now on a further step of calibration. We have put some recommendations for the total work, not this part of which I've presented. The adoption of CBAL now at the ministry, and I think there's a training at the end of this water week for CBAL. There is a use of different techniques of remote sensing, which is recommended. Now we can combine Landsat, for example, with the European Space Agency data of Sentinel-2. Both are available, which means that you will have a medium resolution every 5 to 6 days. You will have a satellite imagery, free of charge, in which you can access. I think Sentinel-2, you can even get something like 10 to 15 meters free of charge. Now we are working with farmers in the next step in the phase 2 of the project with the World Bank. We are trying to select some of the farms in Azraq and in the Highlands to find solutions for the water use. We discovered at the end that there is no solution without working with farmers. So we said, instead of carrying out the monitoring task for the ministry, why not educating the farmer? So now we have applied for the second phase for the World Bank to work with the Highlands Forum. And we are trying to merge some of the remote sensing with the socio-economic data. Now this is another project with FAO, and we have a meeting, I think, tomorrow to discuss this issue. Okay, thank you for your listening.
Thank you very much, Professor Bakri. It was very interesting to see some of the work. And I have a couple of questions, but I will wait until the turn for question comes by. Our third speaker is Dr. Khair Hadidi. Dr. Hadidi has a PhD degree in engineering hydrogeology from St. Petersburg University in Russia in 1992. He is working as Assistant Secretary General for the Groundwater Basins at Water Authority of Jordan. Dr. Hadidi has more than 25 years of experience in water resources management. He's published more than 20 scientific papers. His current activities include participation in water resources management, groundwater well abstraction and water resources investigations, and the development and development.